All right, guys, welcome to this vodcast on SAC2, the tech-free paper. All right, question one was a nice gentle start to the paper. It was a verification paper. It even told you in brackets the technique of verifying. You differentiate and you substitute into the second order DE in this particular case. It's all about matching LHS with RHS. That's what it's about. So I awarded a mark by simply taking that exponential function and differentiating it with respect to x once and then twice, getting the double derivative, and then replacing those expressions into the left-hand side of the equation above, creating a simplified expression and showing that that's the same thing as the expression on the right-hand side by substitution. Finishing with a statement, LHS equals RHS. Now, if you lost a mark here, typically you lost a mark because you didn't follow an adequate verification procedure. You might have mixed terms from one side to the other, which is a no-no. I even tolerated left all, rather than separating the expression for the left-hand side and the right-hand side and then showing a final statement saying LHS equals RHS. If you did it on the one line, I tolerated that, but I didn't like it. But as I said, if you lost a mark here, it was for more setting out and the logic behind verification, which you didn't show. And if you'd like tips on how to get better at that, please don't hesitate to ask. Okay, question two was solving a second order differential equation. Okay, there was the rule and you were told the value of the gradient at x equals 0, y dash of 0 is equal to minus 1, and you're told a point on the curve itself. So when x is equal to 1, y is root 3 pi on 3. Quite a strange sort of y value, but it makes sense when you get there. All right, so how do you do this? You set up an integral expression for dy dx. Okay, so you have to anti-differentiate 6x on top of x squared plus 3 all squared. And most of you were able to recognize the correct method to apply here, method of substitution. Let u equals x squared plus 3, and you can see the denominator is a multiple of its derivative, which is 2x. And so you're able to come up with that line below. I might just grab a pen. You're able to come up with this line over here, which was nice, and it anti-derived quite neatly. Some of you forgot to divide through by minus 1, which was problematic, and you came up with that general expression. And then, of course, what do you do to find the constant of anti-diff? Well, you appeal to the first bit of information given, that when x is equal to 0, dy dx is equal to minus 1, and you got a c value of 0. Now, quite a few of you managed to not read that information carefully and wrote down when x is equal to 0, y dash is equal to positive 1, and got a c value of 2. Some of you wrote it down as minus 1 is equal to c minus 1, and therefore said c is equal to minus 2. I had all kinds of strange answers for this, and it should have been a straightforward approach. All right, moving on. Okay, so what do you do then? Then you solve for y, so you anti-differentiate a second time. So 2 marks for the first part and 3 marks for the second half. So anti-deriving it, you can see if you just take any constant out, you focus on just what's inside the integrand, it can help you. You have a look down here. You have a look at the denominator expression, and you say to yourself, is that factorizable? And it's not, so therefore you know you're going via an inverse tan expression. So what do you need to do? Complete the inverse tan. You need the square root of that. You need the square root of 3 up there. So the square root of the x squared plus that positive term. No need to complete the square, put it into that form, all good to go. So then when you divide through by the square root of 3, you get this as the expression for the antiderivative, and then you replace the x is equal to 1, so you apply the known point on the curve, and then you solve for D. A lot of you fell apart down here at this stage, working out the constant of anti-diff, which was interesting, and you came up with this as your final answer. So yeah, so often a lot of you did the right approaches. You actually did the method of substitution initially. You recognized it was an inverse tan, but you made an algebraic error somewhere down the track. But it wasn't too badly done. All right, question 3. Originally, I didn't have this part. It was designed to help you as much as possible. It was simply anti-derive, or find the area beneath the curve and the x-axis. But then I thought I'd help you and actually have a distinct part, put it into partial fractions. Now, the first thing you have to always, and a lot of you didn't do, was recognize that the polynomial in the numerator, degree 2, is equal to the degree of the polynomial in the denominator. It has to be a proper rational fraction in order to proceed with the partial fractions routine. So because it's not, because it's degree 2 over degree 2, it means you have to perform some sort of division first. So x squared minus 4 into minus x squared plus 9. So you get a quotient of minus 4, remainder minus 7. So we can take minus 4 out, and we can start to focus on this rational fraction as the one we need to resolve into partial fractions. The minus 4 is just the constant we add at the end. Okay, now, even if you didn't pick up on that, you should have seen in the graph below, you have your rational graph, and there was a horizontal asymptote at y equals minus 4. That corresponds with that constant that you see there, is minus 4 plus that improper rational fraction. So it was I gave you the picture largely and the equation of the horizontal asymptote, so you could clue in on the fact that you may have to perform division first. Anyway, doesn't matter if you didn't, it's all about learning. So then you go through the process of resolving it into partial fractions, and it's that straightforward one. 2 distinct linear factors in the denominator, and then you set your a and b, and off you go. It turns out a was 7 on 4 and b was minus 7 on 4, which led you to resolve it in the way you see below. Okay, hopefully that makes sense. All right, so you're told you have to work out the area of that shaded region, okay, as it turns out. So you set your numerator function to 0, and you can see x is plus or minus 3 on 2. In fact, you can see both the numerator and denominator functions are symmetrical about the y-axis, so their quotient will also be symmetrical about the y-axis. So that can simplify the actual calculation of the shaded area. As you can see, that's what I'm doing over here. I'm integrating it from 3 on 2, from 1.5 down to 0, and doubling it, which just lessens the chance of error rather than integrating it from positive 1.5 to minus 1.5. Okay, even if you didn't do it, that's not a problem. However, a lot of you didn't add the negative component, because of course, what are we dealing with? We're dealing with area below the x-axis, which has a negative sign to it, negative signed area. So to work out the area, you need to multiply it by minus 1. So a lot of you were on the back foot from the start. Okay, if you could recognize that, you were good to go. And let's just click ahead. Okay, so you know, the constant becomes negative 4x, so on and so forth. You've got 7 on 4 times natural log, minus 7 on 4 natural log. Always an idea. Okay, so you got a method correctly there. Always an idea to make it a single log. All right, it just simplifies matters. And secondly, the form of your answer had to be as a single log as well. So probably a good idea to make it a single log at that point. Make your substitutions, and off you go. You should have led you to the correct answer. Quite a few arithmetic or algebraic mistakes, fraction errors were made at this point, but that turned out to be the correct answer. Okay, question 4 was an arc length question. So the length of the curve of our f of x function from one value of x to another. But rather than being able to work out that length via alternative means, you were led, according to the question, you were led into using the arc length formula, which is what I wanted you to do. So the first part was simply differentiate. So I think just about all of you got this part right. And so you should have. It's just a straight out math methods chain rule application, and it led you to that answer. Okay, from there it was simply recalling what the arc length formula is. In fact, it's available to you on your VCAR formula sheet, so all of you should have had access to this. Some of you did not write down the rule correctly, which there's really no forgiving that kind of error because it's there in front of you. But what it is the interval, lower bound, upper bound, integral, square root of 1 plus dy dx all squared. So you can see what I'm doing here. I'm going off on the side. I want to get an expression for 1 plus f dash of x all squared. So let's go and do that. We've already worked it out. So we've just squared the result above. Even if you didn't get it, it was given to you. So that's a given, and squaring it is really no big deal. So 1 plus that expression, let's get a singular algebraic fraction out of it. You've got a numerator of 1 minus 4x squared plus 4x squared. The 4x squareds eliminate each other, and you're left with that nice, neat expression for 1 plus f dash of x all squared. I take that expression and I return it to the square root. So the square root of 1 plus f dash of x all squared is simply the square root of 1 over 1 minus 4x squared, and of course that's reduces to the integrand that you see before you. Okay, now hopefully some of you recognized what to do here. A lot of you did, in fact. So that's the length I need to find. That's the integral I need to solve in order to work out arc length. And most of you are on the ball and realized inverse sine is how I need to tackle it. So how do you manipulate the expression to enable a straightforward application of inverse sine? You factor out the 4, which becomes 1/2 outside the integral sign, and then you apply the rule. So inverse sine x divided by 1/2 is inverse sine 2x. We're integrating from minus a quarter to 1/2, and then it's simply your exact values. So inverse sine 1 minus inverse sine minus the half, and leads you down to a final answer of pi on 3. All right, question 5 was a mixed bag. It was looking at a particular differential equation involving a product of x's and y's, so perfectly set up for separation of variables, but it asked you to do some approximation applications initially in parts A and B. The first one was given that when x is equal to 0, y is equal to 1, so you've got to firstly find that point on the slope field, draw the solution curve. Now, I get why this caused some problems, and I apologize in part. Moving to the left, you can see it's got that, oh, sorry, it's a bit out of sync, my stylus, but you can see it's got that curvature to it. Following it down to the left, oops, hang on, let me just get rid of that. Following it down to the left, you can see you approach a flat little line segments, and so some of you did this. And I understand why that would have occurred, because you're not really being corralled as such. But if you have a look above the line, you can see there's a pattern occurring for little slopes, line segments above that flat line. Of course, that flat line would correspond to what? Dy dx is equal to 0 when 4y minus 1 is equal to 0. So when y equals a quarter, so that y value is corresponding to y equals a quarter. But having said that, I couldn't find a better slope field to assist you, so that's the one you were given. And and secondly, in part C, you actually had to come up with the solution curve itself, which was a parabola. So I was hoping that even if you didn't quite know what to do entirely here, that you could realize later on that it was a parabola and go and fix up your error and realize that the slope had to move in that direction. So I was looking for the fact that I was looking for two things: a roughly parabolic shape, and I was looking for the fact that your shape would go through the points 0, 1. So it had to go through that point because that's how you approximate graphically, create a solution curve given 1 point on the curve. Okay. All right. Anyway, so quite a few problems with this, but I somewhat apologize, but at the same time, I think there was good learning involved in the question itself. Okay, moving on. All right, we still know that when x is equal to 0, y is equal to 1 is a point on the curve, but now we're going to use Euler's method to estimate the value of y when x is equal to 1/2, using a step size of 1/4. So how do you employ Euler's method? Of course, that's the known point on the curve. It'll take 2 jumps of 1/4 to reach x equals 1/4. So what we need to do is calculate y2 in the iterated approach of Euler's method. Okay, so you can see what we're doing here. General always pays to write out the general rule. So y1 will be, might just change colors, y0 plus the step size 1/4 times by x0 and y0 replaced in our rule for dy dx, which is up here. So 4 times 1 minus 1 is 3, over 2 times 0 plus 1 is 1, and it leads you to 7 on 4. Okay, and we add 1 to 1/4 and we get our value for x1. That then applies to the next level. Okay, what is our y1? It's our x 7 on 4, h is 1/4 again, and now of course I'm replacing x, so y 7 on 4, and x is equal to 1/4 into the rule. So 4 times 7 on 4 is 7. 7 minus 1 is 6. That's the numerator. 2 times 1/4 plus 1 is 3 on 2, and that's the values you see. 4 times 3 on 2 is 6. 6 on 6 is 1. So at the end of the day, y2 was 7 on 4 plus 1 is 11 on 4, or 2.75. So that's what I was looking for. So it's straight out. Do you know how to apply Euler's method? And it was done okay, I would have to say. Okay, the final part of this question was to solve it. And so I was looking for immediately an expression of this form. Okay, must involve the integral symbols in order to make sense of it. And it's just straight out separation of variables. That first step was done reasonably well. Okay, and in fact, quite a few of you were able to come up with that next line. So just one on the reciprocal of each. So the reciprocal of the coefficients of each of those expressions, straight out log plus c. And then it's always an idea. Some of you delayed this step, working out your c till later. Don't do that, I'd advise. I think it's much better to determine your constant of anti-diff in these separation of variables questions as soon as possible. So when x is equal to 0, y is equal to 1, and of course it leads you, oh, that's 1/4. There it is. Yes, so that should be 3. That should be 3. 4 times 1 minus 1 is 3. And of course, log of 1 is 0. So it leads you straight out to y value of 1/4 natural log 3, which I wrote correctly over here. Okay, let's move along. All right, from there, I think it's an idea to, rather than apply your plug law, just multiply out, try to deal with nice integer values, multiply everything by 4. That's all we're doing over here, is just every term multiplied by 4. And then of course, I can then make a single log expression left and right, and ultimately drop the logs entirely. So log of 4y minus 1 is the same as log natural log 3 brackets 2x plus 1 all squared, just using your log laws, and then I can drop the logs entirely. So now I've just been a bit thorough here. So 4y minus 1 is plus or minus that expression on the right. So because I'm just being quite thorough, and then I'm appealing to the fact that, well, when x is 0, y is 1, so we're going to just reject the negative and equate 4y minus 1 with positive 3 times 2x plus 1. All right, from there, add 1, divide by 4, and you're left with y in polynomial form. Some of you left it in turning point form or other forms. All I really wanted to see was, can you remove the logs and simplify the expression for me? So that's what I wanted as a final answer. Okay, question 6 was a nice application question, but very doable by hand, which was kind of neat. Okay, it's all about foxes decreasing in a national park, at a rate proportional to the square root of their number at any time t years. So that's where this response comes from. So the rate of change of n, the population of foxes, with respect to time is proportional to the square root of n. Okay, then you're given some extra information. After 2 years, the fox population is 25% of the initial population, and we're going to represent n0 as the initial population of foxes. So initial conditions will help us with the constant of anti-diff, and the extra information will help us with the constant of proportionality. Anyway, moving on. So just putting that in terms of a mathematical equation, we bring in k for our constant of proportionality, and it must be negative. Okay, it must be negative because we're talking about a decreasing rate of change. Okay, all right, moving on. All right, determine the number of years it takes for the fox to reach 9% of its initial population. So first thing is, let's begin the solution process. And we've got dn dt as a function of n. So in order to apply our calculus skills, we need to reciprocate that rate of change to dn dt, and off we go. So I was looking for that kind of statement to kickstart the question. Of course, adding 1 to minus a half is a half, dividing by a half is multiplying by 2, leads you to this expression over here. Okay, so we've got two unknowns here, two parameters, two unknown constants, and I always like to involve initial conditions to work out my C, my constant of anti-diff. And of course, what are the initial conditions when t equals 0? N is that n0, the number of foxes initially. So we're going to get C in terms of n0 as follows, which is a simple operation, and then return it into our expression for t, and we've now got t is 2 over k, the constant of proportionality, square root of n0 minus square root of n. Fantastic. Okay, so in fact, let's keep going on to the next page. Okay, so now we're going to appeal to the fact that when t equals 2, n is a quarter of the initial population, n equals n0 on 4, to work out what our k value must be. So making those replacements in the above rule, you can see, well, I can multiply across by k, divide through by t, and I'm left with k value is the square root of n0 divided by 2. Magnificent. We're getting very close to a final answer. So if k is equal to that, then I make that replacement in my general rule for t. Remember, t was equal to 2 over k square root of n0 minus square root of n. So I'm just making that replacement for k over here. Off I go. And okay, and now I'm going to appeal to, well, we need to find t when n is equal to 9% of n0. Okay, so in other words, 9 times n0 divided by 100. All right, why did I choose that? Because it square roots very nicely. So obviously the square root of 9 on 100 is 3 on 10, or 0.3. we're very close to a final answer here. So n naught, square root of n naught minus 0.3 of n naught is 0.7 of n naught. Now the n naughts will cancel. You can see as I've got it shown, and you're left with 4 times 0.7, which is 2.8 years. Okay, neat. That was done okay. Okay, question 7 is the final part of the paper. We're looking at a pair of graphs, both an inverse sine graph and an inverse tan graph, undergone a dilation or two in each case. And the inverse tan graph nicely crosses through the endpoints of my inverse sine graph. So let's just firstly, the first part of this problem concerns my inverse sine graph, the y equals f of x. I might just highlight that for you guys. So here it is. I'll just trace that for you. Oh, actually, let me just redo that. All right, let's try to do it more accurately. So there's the trace, bit wobbly. There we go. Not brilliant, but there you go. There's my y equals inverse sine graph. So let's just highlight what I've just shaded. The second graph, my inverse tan, will come into the second part, so we'll concentrate on that later. But what I do want to focus on is the line connecting all the points of intersection. So let's just trace that line here for you. Okay, so that's the line y equals x. All right. Okay, so that's going to be of significance for us in A part 2. Let's just have a look at A part 1 for a minute. Okay, so A part 1 is simply a definite integral calculation. It hasn't asked you to interpret it at all. Okay, so simply find the definite integral from 0 to pi on 2 for that expression. And a lot of you, in fact, came up with the correct rule, but then when you substituted in pi on 2 and 0, errors occurred and you didn't get the final answer, which was a little disappointing. I mean, that was, math methods level. Most of you should have had no trouble with that. So, all right, so what's the relevance of that for the next part, which is actually finding the area enclosed between f and inverse f? So what does inverse f look like? I mean, we can see visually, it'll be just a reflection about the line. It'll be just a reflection about the line y equals x. And sorry about that, if you heard that was an announcement. So that's obviously the graph of y equals inverse f. Okay, and what would be the rule for y equals inverse f? Well, let's have a think about it. So what we're doing is taking swapping our x's and y's. So x is equal to inverse sine 2y on pi. Let's transpose to make y the subject. 2y on pi will be equal to sine x. Therefore, y is equal to pi on 2 sine x. Okay. So what's there? It is appearing there. So what area is this indicating by this definite integral? So a lot of you hopefully would have come to the realization it's this area in here is what I've just calculated in A part 1. Yep, the area locked between the inverse graph of f and the line y equals x. Now you can see the symmetry involved. If I call this area 1 will be equal in size to area 2, the area below between f of x and y equals x, area 3, and area 4. They'll all be equal in size due to the symmetry. And that was the inspiration behind the next part of the question. Hence determine, so there was a big clue, the area bounded between the graph of f and f of x, it's simply 4 lots of your answer to A. So whatever you had for A, if you did 4 times it, you got the correct answer. Okay, this was the final part of the paper. There was initially another part, simply find the area between the two curves, but I decided to just run with this. Find the volume of solid when one of the bounded regions between F and G is rotated around the y-axis. So before we highlighted we highlighted the inverse sine graph. So let's just highlight that over here. And let's just mark in red the inverse tan graph, which is this one over here. So what happens when this region enclosed between the two is rotated around the y-axis? Okay, so straight away it's again making x in terms of y for both. We've already done that, or you should have already thought about it above, and when answering A part 2, when making x the subject for the inverse tan graph, we get that particular expression. Now, some of you had trouble of understanding the rule. So when I'm calculating the volume of solid, it's pi. Okay, I'm integrating, so the y-axis, it turns out to be the same as the x, so it's from pi on 2 down to 0, so pi on 2, 0. But it's going to be my x is a function. Here's my outer function. This one is furthest away from the axis of rotation. So it's that one squared minus the one closest to the axis of rotation squared. So in other words, I think rather than try to scroll it out, that's what I was looking for. So the volume is pi times pi on 2. The first rule, x is a function of y squared dy, minus the second rule, the inverse tan, because it's closer to the axis of rotation. So the axis of rotation being the y-axis. Okay, all right, so then we need to just square it. You've got a common factor of pi squared on 4, so it's always nice to take that out of the integral symbols. So pi squared on 4 times pi is pi cubed on 4, so everything gets multiplied by pi cubed on 4. Okay, let's see what we're dealing with. We're dealing with a sine squared y. We're dealing with a tan squared argument. Okay, so this was a test of, do you know what technique do you do when it's sine squared or cos squared? And it's all about the double angle rules. So let's just clear off this, and you can see you need to think about your double angle rules. So ultimately we want to be able to relate sine squared to cos 2x, sine squared theta to cos squared 2 theta. We rearrange and we make that replacement. So out goes sine squared y, and in comes 1 minus cos 2y on 2. That divisor by 2 just enters outside the integral sign as division by 8. Notice I've separated the integrals here just for ease of application. And how do you integrate a tan squared expression? We'll use the Pythagorean identity, because the antiderivative of sec squared becomes tan, and that's the way forward when it's tan squared. When it's just tan, then you see it as the ratio of sine to cos, but when it's tan squared, it's the Pythagorean identity. So some of you were not sure what to do there. Moving forward, it just became mechanical from there on in, and you can see it's fairly straightforward from there. And the only errors that were made, actually quite a few errors were made just by sloppy algebra or sloppy fractions work. So marks seem to go by just carelessness at this point. So a lot of you coming into the final exams will need to really work hard at making your algebra and your fractions work and your by hand work as tight as possible. But let's keep going. If we go over the page, you can see it's just making those straightforward replacements. You've got x cubed and x cubed. You've got pi to the power of 4 and pi cubed, so you collect your like terms and you put it into the final expression. And there is your final answer, and there is the end of the paper, which we're always happy to see when we get there with some time remaining on the clock. Okay, that's it for Tech Free. Stay tuned for Tech Able. Bye for now.